the conservation of momentum part 1 video. So I'm going to talk a little bit about the theory of the conservation of momentum. Now we learned earlier that impulse equals change in momentum, which is final momentum minus initial momentum. Okay? And the analogy that I want to use with this is kind of like work equals change in energy. Kind of the same idea, right? Same analogy, right? Now, when we worked with the work energy theorem, I think the way I told you to write it is like this. Okay, it was like the initial energy plus total energy, mechanical energy, plus work equals final energy. In other words, work will change your energy level. Well, I'm going to do the same thing here because sometimes it's easier to work with it in this other form that I'm going to come up with. So which is PF, okay, equals, or actually PI plus any impulse equals PF. Okay. Now, we say that mechanical energy was conserved when we talked about energy when there is no external work. So if there is no external work, the energy initial equals the energy final, and you can solve your problems. In here is the same idea. Momentum is conserved if there is no external impulse. In other words, there are no external forces acting on the body or the system, in other words. Okay? Because we have to decide what our system is going to be. Okay. So here, if there is no impulse, I can say that the initial momentum equals the final momentum. That's when we'll do a lab, we're going to have to try to measure the momentum, okay, before a collision and the momentum after the collision, immediately after, and immediately before. Because once you allow other external agents to be involved, the momentum is no longer conserved. And if we have two objects that are colliding or separating, we're going to look at any interaction between these two objects as an internal force. Okay? It's just like, it's kind of like similar to when we did the Atwood machine, and there were times when we looked at the tension as an internal force. That's kind of like the same idea. So if we're looking at the system as being all the objects interacting with each other, all the interactions between them are considered internal, and there is no external impulse. The impulse is kind of like within the system. So this is basically the law of conservation of momentum. And that's true if there is no external impulse. Okay. Now this is a vector quantity. This expression is a vector quantity, which means if momentum is conserved, it's going to be conserved in all dimensions. Meaning, like if this is a 3D problem, it will be conserved in the x, the y, and the z direction. But here we're just going to stick with momentum in 2 dimensions. But for now, I'm going to start with momentum in 1D, meaning like the object will just move right or left, or the objects, or they will move up and down. Nothing in between. They will not move in the x and the y direction. So in this case, we're just going to drop the arrows, the vector the concept behind the conservation of momentum. So I'm going to start with some problems here. Okay. So I have some problems that I want to try. So let's just say I have object 1, and it has a mass of 2 kilograms, and it's going to collide with object 2 that has a mass of 1 kilogram, and this guy is going at 5 meters per second. This one is going at 2 meters per second. Okay, and so right before they collide, these are their speeds. Now the collision happens, so this is before the collision, and this is going to be after the collision. Now after the collision, this one slows down to 3 meters per second, right? And it still has 2 kilograms. Okay. Now I want to try to figure out what's happening to the 1 kilogram object. Okay? All right, so let's try this. So the momentum of this guy, I'm going to look at the momentum of the whole system. The total momentum, in other words. The same way we did with energy, we looked at the total energy. So the momentum of this is m of mass of object 1 times the velocity of 1 plus m of object 2 times the velocity of object 2 equals, and you see that since they are in one dimension, I'm not going to use the vector notation here. So this is going to be m1 v2, I'm sorry, v1. Anything that's after the collision, I'm not going to call it final, I'm just going to say prime here. Okay, plus m2 v2 after the collision. Okay, now they don't stick together, they separate. Okay, m1, this is 2 times 5 plus 1 times, now if you know, if I'm going to choose right as positive, so I can see that this object 2 is moving to the left. So that's a velocity of negative 2 equals 2 times 3 plus 1 times v2 prime. And you can solve this equation and you can get your velocity, the velocity of the 1 kilogram object. Okay? All right, let's change a couple things here. So I'm going to look at different scenarios here. Second scenario is that I'm going to make this object go to the right at 2 meters per second, and right, and I'm going to leave everything else as is. So again, after I write my formula with the variables, so I can see that this is 2 times 5 plus this time 2 times a positive 2, because the 2 is going to the right, equals 2 times 3 plus 1 times v2 prime. And you can find your velocity. Let's see what we get. 10, that's 14 minus 6, so that's, is that 14 minus 6, that's an 8, right? Yeah. Okay, so that guy will be going at 8 meters per second. Okay. All right, let's look at another case where I'm gonna make this one 20 kilograms. I'm gonna make this one go at 1 meter per second this way, and I'm gonna make them stick together. So after they collide, they become one piece. Okay. So basically, you have 22 kilograms here. So here you should have two terms for the total momentum. Here you should only have one. Okay. So this is going to be plus 20 times negative 1. Yeah. So the total mass there is 22 v prime, or you can call it v1, 2 prime, whatever you want to do. So v prime is going to be 10 minus 20, so that's negative 10 over 22 meters per second. I think I did the math right. Yeah. Okay. The next case that I'm going to do is explosions. So I'm going to have an object. It's the opposite of when they come together, when they stick. So I'm going to have an object. Let's say it has a mass of 6 kilograms. Okay. Let's just look at it at rest. So it's not moving, and it's an internal explosion, and it breaks into two pieces. One piece has a mass of 1 kilogram, and I really don't know with what speed it's moving, and the other piece has is going at 8 meters per second, and has the whatever mass is left, which is 5 kilograms. You don't lose mass. All right. So if this is at rest, its total momentum is 0, equals. Now you can see clearly that the momentum of the 1 kilogram and the momentum of the 5 kilogram have to be equal in magnitude. There is no other way around that. They have to be equal and opposite, so that when you add them together, you end up with a 0. So the momentum of these two, the momenta of these two are equal, right? If the momenta are equal, the 1 kilogram, since it's lighter, has to travel faster than 8 meters per second. It's all proportional, right? And I think we did this with Newton's third law. The object with the smaller mass will have to go faster. All right, so this is going to be, I'm going to call this one 1, I guess, and this one 2. So this is going to be the mass of 1 times v1 prime, I really don't know what that is, plus 5 times, the 8 is going to the right, so positive 8. So v1 prime is going to be equal to, it looks like negative 40 meters per second. Yeah, they have different speed, but the same momentum, right? But opposite in sign. Okay. Now let's try to say that this object was initially moving at 4 meters per second, and as it's moving, it just breaks into two pieces. So the momentum here, and this is after you write the equation, of course. This is going to be 24 equals, and you can look at the answer key for how the work is done. It's going to be the mass of one got my microphone. Okay. The mass of one times the velocity of 1 prime plus the mass of 2, the velocity of 2 prime. So this is 24 equals, this is 1 times v1 prime plus m2, which is 5 times 8, positive 8. v1 prime equals, so that's going to be 24 minus 40, that's negative 16 meters per second. Okay? So now the momentum of this is 40, right? And the momentum of this here is 16, right? So here they are not equal, and the reason for that, because this was initially moving. If it was at rest, they have to be equal. So you just have to be careful with that. If this is not moving, that's when they are equal to each other. Okay. Now I'm going to talk about different kinds of collisions. Okay. You have elastic, and I'm going to have a video just talking about the elastic collisions. And you have inelastic, and you have perfectly or totally inelastic. Okay. With elastic collisions, for all of these three, as long as there is no external impulse, momentum is conserved. So for all three. Okay. For elastic, kinetic energy is conserved. Okay. For inelastic, the kinetic energy is not conserved. Okay. But the objects do not stick together. In other words, the collision happens, there's some loss of energy, right? Whether it's in the form of heat or sound or some other form, but the objects separate after the collision. Okay? There is a perfectly inelastic collision, which the kinetic energy is not conserved, but the objects stick, right? So elastic, I'll give you an example. If you play in pool, the collision between the balls is basically as close as the elastic as you can get, right? Because the shape of the balls does not change, and the collision happens for a very quick amount of time. Okay. Inelastic is like a car accident where the cars hit each other, but they don't stick together, right? So there's a lot of loss of energy to kinetic energy to heat. And then the last one is like if you have an accident where the cars hit each other and they stick together. So a lot of that energy is going into heat, is going into changing the shape of the two cars. So those are the three forms of energy, and it will be a video just for elastic collisions. And for elastic collisions, okay, the one thing I want you to remember about elastic collisions, so if you have an object moving at a velocity v1, and then another object moving at a velocity v2, okay, this is before they collide. After they collide, they're going to be going at v1 prime and v2 prime, okay? One thing you have to remember, and what I'm going to tell you is only true for one dimensional collisions. I'm going to prove to you that v1 minus v2 equals v2 prime minus v1 prime. Okay, so you can add this equation to the conservation of momentum to solve for other things, because with elastic collisions you might have to look for two variables. So one equation will be right here, and the other equation will be the conservation of momentum. What this actually means is that the relative speeds, okay, of the two objects, the speed, each object with respect to the other is the same before the collision and after the collision, with a difference in sign here, okay? Because technically I can write this as negative v1 prime minus v2 prime, okay? So you can see that the relative speed is the same. So I'm going to finish here with maybe 2 examples. All right, so we don't need this. We already know this stuff. So actually, I'll finish with 1 example. I'll leave the other one for class. So it's not the best circle, but okay. I want it to be more flat here, but got the idea. Okay. So I'm going to make this radius 1 meter. I'm going to have a block here that's 1 kilogram, and it's starting from rest. So I'm going to call this object 1, and down here is object 2, and it has a mass of 0.5 kilogram. Okay, this one starts from rest. Okay, and the distance between them, the vertical distance between them, is about 1.8, or exactly 1.8 meters. This object here is 6 meters above the ground, and so a couple things we can do here. I can try to figure out the normal force up there. I can try to find the normal force up there, which is also called the apparent weight. Or I can find the normal force here. So I can label these points A, B, and C. Let's just say we get here and we encounter some friction. So this surface here has some friction here, okay? And there's a cliff here. So this distance here is 20 meters. I want to find the coefficient of friction so that this object gets right here, okay, and stops. It doesn't get off. It doesn't go past the cliff, right? So it stops right there. So I want it to stop here. I'm actually going to do it for which one? I'm going to do it for object 2. Okay, and if one has more kinetic energy, by the time it gets here, it will hit it and they will both go flying as horizontal projectiles. So let's try this. So this is basically going to start sliding. Let's say you have a mechanism here. As soon as this hits, as soon as one hits 2 just gets going, right? But for now, it's just sitting on a frictionless surface, and something is stopping it. And let's see what we can do here. So when this is sliding, I want to know its speed right before it hits it, right? Okay, so I can do 1/2 m v square equals mgh. Okay, and I'm talking about object 1. I'm sure I did. So maybe this is 1.8. You got the idea, right? All right, so this mass is gone. This is 10 times 1.8 equals 1/2 times v squared. So the moment it's going to hit it, or v1 squared, that's going to be 6 meters per second. So block 1 is going to be going at 6 meters per second. So I'm going to do conservation of momentum. Okay. All right. So before I do that, I'm going to give you a graph. Of time in milliseconds and force in newtons, and I'm going to say that this is about 200 newtons. Okay, so I think I can figure out the impulse delivered to the half kilogram mass just by finding that area. So when this collision happens, the impulse or a force versus time graph, force acting on number 2 is given by this graph here. So now we know that an area under the curve or between the curve and the time axis in an FT graph gives us the impulse. So if I find this area, I get an impulse equal to 5 newtons times seconds. So now I'm going to try to figure out do the conservation of momentum or the momentum impulse theorem and see what we can what the speed of this guy would be. So let's try that. All right. So this had no momentum, right? Plus any impulse equals the final momentum. So that's going to help me find its speed. So I'm doing pi plus impulse equals pf. So there's no initial momentum. There's some impulse. I want to find the final momentum. So this is 0.5 times the velocity of 2. Okay? So the velocity of 2 is going to be equal to 10 meters per second. So after the collision, this guy will be going at 10 meters per second. Okay. Well, what will be the speed of the 1 kilogram mass after the collision happens? Well, I can do these 2 different ways. Okay, so I'm done with this. I can do these 2 different ways. I can say, well, the initial momentum for number 1 plus any impulse applied to number 1 equals final momentum of number 1, right? So right after the collision, I mean. Okay, so before the collision, we know the momentum. So that's going to be the mass, which is 1 times the velocity. Now, if this one gets an impulse of 5, according to Newton's third law, the 1 will get an opposite impulse. So the impulse of 1 will be negative 5. So you've got to be careful with that. Equals 1 times V2, I guess, or V1. V1, after the collision. So I can say that it's after the collision. All right, so this one is going at 10, so let's figure out what this one is going to be going at. This is going to be going at 1 meter per second. Let me just make sure that's what it is. Yep, should be going at 1 meter per second. So this one is going to be going after the collision, that is, right? So maybe I should have it down further. So 1 meter per second after the collision. So anything in red is after the collision. I could have done this differently. Okay. So if I want to find the speed, so I don't need this. If I want to find the speed of object 1, I could have just done the conservation. Okay, I can say, you know what? This one had a velocity right before the collision of, so the mass is 1, had a velocity of 6. We did that with the conservation of energy. And we're going to look at the interaction between them as internal. Okay, so the momentum before equals the momentum after. The second one had nothing, equals the momentum after. So the 1 kilogram, I don't know its speed, v1 prime, I guess, plus we calculated the speed of this one from the graph, from the FT graph, plus 0.5 times 10. So this is going to be 6 equals v1 prime plus, that's a 5. So we should get 1. So you can do it 2 ways. You can do it from the FT graph. Just make sure you consider it to be negative. Because even if you did consider that momentum exerted on 1 as positive, you're going to see that the speed of this, okay, will be higher than 6, which doesn't make sense. It should be less. Okay. All right, so now that we have this, I'm just going to concentrate on 2. Whatever I'm going to do for 2 is kind of like similar to what you're going to do for 1. And you can also think about this. Well, what happens if they hit and they stick together? So I'll do that like in a few minutes, but for now, let's just say they separate. So when we are down here at the bottom of this hill, I can do conservation of energy here. So I can do mg, I'm working with the object, so mgh equals half mv squared. And there is a kinetic energy. We're starting with some kinetic energy earlier. So now you can find the speed here, which I already done, so I don't have to waste time. That's going to be down here, you're going to be going at 14.83 meters per second. I also did the velocity at the top. Velocity at the top is going to be, if you do conservation of energy, so you started with, you can do it two ways. You can start from down here. So you say kinetic energy here equals kinetic plus potential energy here, or you can start from up here. You say kinetic plus potential here equals kinetic plus potential and energy here. So you do it any way you want. 13.42 meters per second. Okay. You can also do that at this point here. Okay. You can do the normal force, which we're not going to do, so we're going to do it quickly here. So the normal force is going this way, the mg is going down. Okay, so the speed right at this point is the same as the speed at this point. Here you have your mg going down, and you have your normal force also going down. Here at point B, you have the normal force going left and the weight going down. So at point B, the centripetal force is made out of the normal force only. So in this point here, it's going to be just N equals, or Fn equals mv at b square over the radius, which is 1 meter. Oops. Okay, so now let's say, when we're here, we move in at 14.83 meters per second. And I forgot to say that this is all frictionless until you get to this point here. You probably noticed that when I did the conservation of energy. So when I'm here, all my energy is in the form of kinetic energy. So it's going to be 1/2 mv right there square, so 14.83 square, plus the work done by friction, which is negative mu mg times d. So I'm just going to put the numbers here. I'm going to leave the m out because that's going to cancel out. Mu mg times d cosine of 180, that's already here, equals, there's no energy at the end. It stops, 0. And then from here, you can get rid of the mass, and you can find your mu to be 0.55. Yeah, 0.55. No units. All right. Now, if this continues, it becomes a horizontal projectile, and you can do energy, you can do kinematics, whatever. All right. So let's just say if these objects stick together, it's the same process, right? Except now, if they stick together, let's see what we get here. Okay. Right here, this guy is going at 6 meters per second. Okay. So I can say that the momentum of this one is mass times velocity plus this guy has nothing in the beginning equals, now when they collide and they stick together, I can figure out their combined speed. So that's going to be a mass of 1.5 times v prime. So v prime will be 6 over 1.5, and I think it's 4 meters per second. So now they go together at 4 meters per second, and you can do your thing over here, and you can figure out what the mu is going to be. Or if you are given the mu, you can figure out with what speed they're going to have here, okay, so that they go flying at as a horizontal projectile. And that should do it for this video, right? So the next video will be about the answers to this video here, and then I'll do one more video that's going to be about the momentum in 2 dimensions. Okay, so 2D momentum, and we're good. And we'll talk about impulse in 2D also. That's it. So I'm going to ask you, you're going to have to watch this, and then I'll put up another video just for the proof that the relative speed, okay, in one-dimensional, in an elastic collision, the relative speed of the 2 objects is the same. In other words, the speed with respect to each other. Have a nice day.
All right, I'm out. Peace.